What if I told you that the edge of the universe isn't just a distant, empty void, but a place where the very laws of reality begin to unravel? Picture this. Light travels billions of years across the cosmos, carrying secrets from regions so far away that time itself seems to bend. And yet, when we peer into those unimaginable distances, we're met with questions so profound they shake the foundations of what we think we know. This is where the ordinary rules of physics twist into something strange, where galaxies behave in ways that defy explanation, and where dark energy silently pushes the universe apart at speeds we can't even comprehend. The cosmos has always been the ultimate mystery, but its edges hold enigmas that even the brightest minds can't fully decipher. Why does the universe appear to be expanding faster than it should? What lurks in the vast, uncharted spaces between galaxies? And how can something as simple as light reveal clues about phenomena that shouldn't exist? These aren't just scientific curiosities, they're cosmic riddles that force us to rethink everything we thought was true. Every discovery at the edge of the known universe peels back another layer, revealing just how little we truly understand about the fabric of reality. Today, we're venturing into the unknown, exploring 30 of the most baffling mysteries that dwell where space and time seem to lose their meaning. From phantom galaxies that vanish without a trace to the eerie whispers of dark matter tugging at the edges of perception, each one of these phenomena challenges our grasp of the cosmos. This isn't just a journey through space, it's a voyage into the deepest questions humanity has ever asked. So buckle up, because by the end of this, you'll see the universe in a way you never have before, and you might just question everything you thought you knew. So what exactly stops us from seeing beyond the observable universe? The answer lies in something deceptively simple: the speed of light. Even though light moves at an incomprehensible 300,000 kilometers per second, the universe has been expanding for so long that some regions are so far away their light hasn't had enough time to reach us yet. Think of it like standing in the middle of an endless dark ocean holding a lantern. No matter how bright your light shines, there are distant shores too far for its glow to ever touch. That's our cosmic horizon, the farthest point where light from the early universe has finally arrived after traveling for over 13 billion years. But here's the twist: the universe might actually be infinite, but we'll never know for sure because everything beyond our cosmic horizon is forever hidden from view. The expansion of space itself stretches those distant regions away faster than light can bridge the gap, locking those mysteries away like pages torn from a book. And this creates a haunting question: if we can only observe a tiny bubble of reality, does that mean the true nature of the universe is something we'll never fully grasp? Astronomers call this the observable universe, a sphere centered on us, stretching 46 billion light-years in every direction. But don't let that fool you. It doesn't mean we're at the center of everything. No matter where you stand in the cosmos, you'd see your own 46 billion light-year bubble with its own unreachable edges. It's like being trapped in a hall of mirrors where every reflection tells a different story of how space and time began. And that leads to something even stranger. The universe might not have an edge at all. Some theories suggest that if you could travel far enough, space would curve back on itself like the surface of a balloon, finite but without borders. So the very idea of an edge might be nothing more than a trick of perspective, a limit not of the cosmos itself, but of our ability to perceive it. That's the paradox of our universe, seemingly boundless, yet forever just out of reach. Somewhere beyond the Milky Way, hidden in the shadows of the cosmos, an invisible force is pulling thousands of galaxies toward it like a cosmic puppet master. This is the Great Attractor, a gravitational anomaly so powerful that entire galaxy clusters drift toward it at speeds of over 2 million kilometers per hour. Imagine floating in space and feeling an inexplicable tug, dragging you toward something you can't even see. That's exactly what's happening to our local galactic neighborhood, and scientists are still scrambling to uncover what's behind this mysterious pull. The strangest part, the Great Attractor lies in a region called the Zone of Avoidance, an area of the sky obscured by the thick dust and stars of our own galaxy's plane. It's like trying to study a shadow hidden behind a blinding spotlight. Even our most advanced telescopes struggle to see through this galactic interference, leaving us with tantalizing clues but no clear answers. Some researchers think this unseen force could be an enormous supercluster of galaxies, while others speculate it's something far stranger, like a concentration of dark matter so dense it warps the fabric of space itself. Then there's dark flow, an even more puzzling phenomenon where entire clusters of galaxies seem to be streaming towards something beyond the observable universe. It's as if the Great Attractor is just the first ripple of a much larger current, a cosmic undertow pulling everything toward an unknown destination. Could this be evidence of other universes exerting gravitational influence on ours, or is it a sign that our understanding of gravity itself is incomplete? Every observation raises more questions. If dark flow is real, it challenges the very principle that the universe should look the same in all directions. Instead, we're seeing hints of a lopsided cosmos where invisible forces are shaping the large-scale structure of everything we know. The Great Attractor might just be the tip of the iceberg, a clue that our universe is part of something far grander and far more mysterious than we ever imagined. So while we can't yet see what's pulling us in, one thing is certain: the Great Attractor isn't just a curiosity. It's a cosmic wake-up call, reminding us that even the most fundamental forces in the universe still hold secrets we've barely begun to unravel. Dark energy isn't just some abstract concept, it's the invisible hand ripping the universe apart at its seams. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, the dots move away from each other, not because they're traveling across the rubber, but because the space between them is stretching. Now picture that balloon expanding faster and faster, as if some unseen force were pumping air into it at an accelerating rate. That's dark energy in action, pushing galaxies away from one another so violently that eventually even the closest stars could vanish beyond an unreachable horizon. What makes this even more unsettling is that we have no idea what dark energy actually is. It makes up roughly 70% of the universe's total energy, yet it leaves no trace, no light, no particles, no detectable signature except for its relentless push against gravity. Some theories suggest it could be a property of empty space itself, a cosmic repulsion woven into the fabric of reality. Others propose it's an entirely new force of nature, something beyond the physics we know. But here's the kicker: the farther we look, the more we realize dark energy wasn't always in control. For billions of years after the Big Bang, gravity held the upper hand, slowly pulling matter together. Then, around 5 billion years ago, something flipped. Dark energy took over, and the universe's expansion began speeding up, as if a cosmic switch had been thrown. If this acceleration continues unchecked, the future of the cosmos looks bleak. Galaxies already on the edge of our observable universe are being pushed away so quickly that their light will eventually fade from view, leaving future astronomers with a night sky nearly empty of stars. Over trillions of years, even nearby galaxies will vanish beyond an unreachable horizon, their light stretched into oblivion by the relentless expansion of space. The universe will grow colder, darker, and more isolated, a vast, lonely expanse where civilizations, if any still exist, will see only their own galaxy adrift in an endless void. But dark energy's grip might not be permanent. Some models suggest it could weaken over time, or even reverse into a crushing collapse, a big crunch where the universe implodes back into a singularity. Others speculate it could grow stronger, tearing apart galaxies, then stars, and eventually even atoms in a catastrophic big rip. The truth is, we're grasping at shadows, trying to decode a force that refuses to reveal itself. Every telescope, every simulation, every equation brings us closer to the edge of understanding, only for dark energy to slip through our fingers once again. One thing's certain, the fate of the universe hinges on this mystery, and right now, the answers lie just beyond the limits of our comprehension. Deep in the constellation Boötes lies a cosmic nightmare, a gaping hole in the universe so vast it could swallow 1,000 Milky Ways without a trace. The Boötes void spans 330 million light-years, a staggering emptiness where galaxies should be cluttered like stars in the night sky. Instead, researchers have found only a handful of lonely galaxies drifting in this incomprehensible darkness, like a few grains of sand scattered across a football field. How does something this colossal, this empty, even exist? One leading theory suggests the void might be a fossil from the universe's infancy, a bubble left behind when quantum fluctuations in the early cosmos created uneven patches of density. Picture boiling water. Most of the pot bubbles and churns, but here and there a pocket of stillness forms. On a cosmic scale, that's the Boötes void, a relic of primordial chaos where matter never condensed into the galaxies we'd expect. But not everyone's convinced. Some astronomers argue that even this explanation doesn't fully account for the void's jaw-dropping scale, sparking wilder ideas. Could it be the footprint of an unfathomably advanced civilization that harnessed the energy of entire galaxies, leaving behind a vacuum, or evidence of a collision with another universe, a bruise on the fabric of our own? What makes the void even stranger is how it breaks the rules of large-scale structure. The cosmic web, the delicate filamentary scaffolding of the universe, should prevent such extreme emptiness. Galaxies are supposed to cluster along invisible threads of dark matter, drawn together by gravity's pull. Yet the Boötes void laughs at these expectations, a cosmic anomaly where the map of reality seems torn. Even its few resident galaxies behave oddly, their shapes distorted as if some unseen force has stretched them toward the edges of the abyss. Then there's the chilling implication. If voids like this exist, could there be others, even larger, lurking beyond our current view? Some models suggest the Boötes void might not be alone, that the universe could be pockmarked with similar emptiness on scales we can't yet measure. It forces us to confront a humbling truth. The more we explore the cosmos, the more we realize how much of it defies explanation. The Boötes void isn't just a curiosity. It's a cosmic riddle written in negative space, daring us to question everything we think we know about how the universe works. Stretching across 1.8 billion light-years near the constellation Eridanus lies one of the most baffling anomalies in the cosmos, a chilling cold spot in the afterglow of the Big Bang itself. When scientists mapped the cosmic microwave background, the faint echo of the universe's birth, they expected subtle temperature variations, tiny ripples in the fabric of space-time. But nothing prepared them for this, a region so profoundly cold it defies conventional explanation, as if a cosmic freezer door had been left ajar in the depths of space. At first glance, the most straightforward explanation seemed to be the Eridanus supervoid, an enormous, sparsely populated region of space where the lack of galaxies and matter could theoretically leave the CMB slightly cooler. But here's the twist: the void size and the cold spot's temperature drop don't quite match up. The math suggests this void should only cause a subtle dip, not the staggering cold we observe. It's like expecting a gentle breeze to explain a hurricane. Something doesn't add up. This mismatch has fueled wilder theories, including the spine-tingling possibility that the cold spot might be a bruise from a collision with another universe. Imagine two soap bubbles brushing against each other in a cosmic foam, our universe and a parallel one briefly touching, their interaction draining energy from our CMB in a way that leaves behind this eerie, frozen fingerprint. It's a radical idea, but it's not pure speculation. Some models of multiverse theory predict exactly this kind of imprint, a shadow of another reality bleeding into ours. Of course, skeptics argue it could just be a statistical fluke, an improbable but natural fluctuation in the CMB's texture. After all, the universe is vast and randomness can sometimes look like design. Yet the odds of such an extreme cold spot appearing by chance are astronomically low, roughly 1 in 50,000. That's like rolling a dice and getting the same number 50,000 times in a row. Possible, technically; probable, hardly. The debate rages on because the implications are staggering. If the cold spot is evidence of a multiverse, it would be the first tangible clue that our cosmos is just one page in an infinite book of realities. But if it's just a void, then we're forced to admit there's a gaping hole in our understanding of how these cosmic structures interact with the CMB. Either way, the Eridanus cold spot is more than a curiosity. It's a crack in the foundation of our cosmic knowledge, and prying it open might just reveal truths we're not yet ready to face. Imagine living in a cosmic desert, a sparse, sprawling region where galaxies are few and far between, and the space between them stretches far wider than it should. This isn't science fiction, it's a reality we're facing right here in our own cosmic backyard. Astronomers call it the KBC void, a colossal bubble of relative emptiness spanning 2 billion light-years, with our Milky Way sitting somewhere near its center. And its existence throws a wrench into one of cosmology's most fundamental assumptions, the cosmological principle, which states that on large scales, the universe should look roughly the same no matter where you are. So why is this void such a big deal? Think of it like standing in the middle of a vast, sparsely populated plain and trying to judge the density of a forest by looking only at the trees immediately around you. If you didn't realize you were in an unusually empty area, you might wrongly assume the entire world was just as barren. That's the problem with the KBC void. It's so enormous that it distorts our measurements of the universe's expansion rate, known as the Hubble constant. If we're inside a local underdensity, our view of distant galaxies could be skewed, making the cosmos seem like it's expanding faster than it really is. Here's where things get even more puzzling. For years, scientists have been locked in a heated debate over the Hubble constant, with different methods yielding conflicting results. Some measurements, like those from the cosmic microwave background, suggest a slower expansion rate, while observations of supernova and other nearby objects indicate a faster one. Could the KBC void be the missing piece of this puzzle? If we're floating in a bubble of lower density, gravity's grip on the surrounding matter would be weaker here, meaning galaxies near us would be racing outward slightly faster than they should be, throwing off our calculations without us even realizing it. This raises an unsettling possibility. What if the universe isn't as uniform as we've always believed? The cosmological principle is the bedrock of modern astronomy, the assumption that lets us extrapolate the behavior of the entire cosmos from our limited vantage point. But if the KBC void is real and as vast as some data suggests, it could mean the universe is far lumpier than we thought, with dense clusters and vast voids on scales we never anticipated. And the implications don't stop there. If the void is influencing our measurements, it could mean dark energy. The mysterious force accelerating cosmic expansion isn't as dominant as current models predict. Or worse, that we've been misinterpreting its effects entirely. Suddenly, a simple underdensity of galaxies isn't just a curiosity. It's a potential paradigm shift, forcing us to question whether we've been reading the universe's story all wrong. Yet not everyone is convinced. Some researchers argue the KBC void's existence is still up for debate, pointing out that galaxy surveys might not be comprehensive enough to confirm such a massive structure. Others suggest that even if the void is real, its impact on the Hubble constant might be minimal compared to other unknown factors. But whether it's a minor bump in the data or a cosmic game changer, one thing is clear. The KBC void is yet another reminder that the universe loves to defy our expectations. The farther we look, the more we realize that even our most basic assumptions might be built on shaky ground, and the answers we seek could lie hidden in the emptiest places of all. If you thought the universe was random, think again. Buried in the faint afterglow of the Big Bang lies a pattern so bizarre it's been dubbed the axis of evil, a mysterious alignment of cosmic microwave background fluctuations that eerily line up with the plane of our solar system. It's as if the universe's oldest light is subtly nodding toward us, whispering that something fundamental might be off in our understanding of reality. This isn't just a minor statistical quirk. The cosmic microwave background, or CMB, is the oldest snapshot we have of the universe, a baby picture from when it was just 380,000 years old. Scientists expected its temperature variations to be scattered like random static, a chaotic symphony of hot and cold spots from the universe's violent infancy. Instead, they found something unsettling. These fluctuations aren't entirely random. Some appear to align along an axis that suspiciously mirrors our solar system's ecliptic plane. The odds of this happening by chance, less than 1 in 1,000. So what's really going on? One camp argues it's just an illusion, a trick of measurement bias or incomplete data. After all, our view of the CMB isn't perfect. Galactic dust and foreground interference could be warping our perception, like trying to read a fingerprint smudged by fog. But even after accounting for these factors, the alignment persists, gnawing at the edges of cosmology's most cherished principle, that the universe has no preferred direction, no special place. Then there's the far more radical explanation that the axis of evil is a fossil from before the Big Bang. Some theories suggest our universe might have inherited structures or imprints from an earlier cosmos, like wrinkles in space-time passed down through a cycle of cosmic deaths and rebirths. Imagine finding a message etched into the foundation of your house, written in a language older than civilization itself. That's the scale of what we might be dealing with, an echo from a time we can't even conceive. Others wonder if this axis hints at something even stranger, a flaw in the fabric of relativity itself. Could gravity behave differently on cosmic scales, warping the CMB in ways we haven't yet modeled? Or is it evidence of an undiscovered force bending the universe's structure like an invisible hand? The very existence of this alignment forces us to confront an uncomfortable truth, that the universe might not be as uniform or as indifferent to our existence as we once believed. For now, the axis of evil remains one of cosmology's greatest unsolved riddles. It taunts us with the possibility that our place in the cosmos isn't entirely accidental, that the universe might carry secrets written not just in its vastness but in its symmetry. Until we crack this code, it stands as a chilling reminder. The deeper we look, the more the cosmos seems to know we're watching. The Hubble tension isn't just a scientific disagreement. It's a cosmic screaming match between two ways of measuring the universe, and neither side is backing down. On one hand, we have the cosmic microwave background, that ancient light from the dawn of time, telling us the universe is expanding at a certain speed. On the other, observations of supernova and pulsating stars in our cosmic neighborhood insist it's racing outward much faster. It's like checking your car's speed with two different gadgets. One says 60, the other 80, and realizing one of them might be broken or that the road itself is changing beneath you. The strangest part, both methods are rock solid in their own right. The CMB approach is like reading the universe's birth certificate, using Planck satellite data to calculate how fast infant galaxies should have spread apart based on the Big Bang's echo. Meanwhile, the supernova method acts as a cosmic speed gun, clocking how quickly exploding stars in nearby galaxies are fleeing from us. These shouldn't contradict each other, yet they do by nearly 10%. That gap might sound small, but in cosmology, it's a chasm wide enough to swallow our current understanding of physics whole. So what's really going on? One possibility is that dark energy, the mysterious force stretching the universe apart, isn't constant after all. Maybe it's been growing stronger over time, like a spring slowly tightening, which would explain why today's expansion outpaces early universe predictions. Alternatively, there could be an undiscovered particle, some shadowy relic from the cosmos's first seconds, subtly altering how gravity works on galactic scales. Or, and this is where it gets mind-bending, our measurements might be skewed because we're inside a vast cosmic void, a bubble of lower density warping our perspective like a funhouse mirror. The implications are staggering. If the tension holds, it could mean we're missing an entire chapter in the rulebook of reality, a hidden force or flaw in Einstein's relativity that only reveals itself across billions of light years. Some theorists are even flirting with the idea of early dark energy, a temporary surge of repulsive gravity in the universe's first moments that left fingerprints we're only now detecting. Others suggest that space itself might be slightly lumpier than we thought, with invisible variations in density throwing off our cosmic math. Every new observation deepens the mystery. The James Webb Space Telescope's pristine views of distant galaxies recently confirmed the supernova measurements, doubling down on the discrepancy. Meanwhile, fresh analyses of the CMB refuse to budge, leaving us with two irreconcilable truths. This isn't just academic nitpicking, it's a sign that the universe might be playing by rules we haven't discovered yet. The Hubble tension isn't a problem to solve, it's a doorway, and what lies beyond could rewrite physics as we know it. We know the universe is made of things we can see: planets, stars, galaxies, and things we can't, like dark matter. But there's another mystery lurking in the shadows. Half the universe's ordinary matter has gone missing. That's right, about 50% of the protons, neutrons, and electrons that should exist based on our calculations are nowhere to be found. These missing baryons, the building blocks of everything tangible, are the universe's greatest game of hide and seek, and their absence shakes our understanding of where and what matter really is. For decades, scientists tallied up all the visible matter in galaxies, clusters, and gas clouds, only to come up staggeringly short. The numbers didn't just have a small gap, they were off by the mass equivalent of trillions upon trillions of suns. Where could so much material vanish? One leading suspect is the cosmic equivalent of fog, the warm, hot intergalactic medium, or WIM. Picture this: threads of gas, superheated to millions of degrees but so diffuse they're nearly invisible, stretching between galaxies like a ghostly spiderweb. This gas isn't cold enough to glow brightly, nor dense enough to block light, making it nearly undetectable with traditional telescopes. It's only when we look at the X-ray shadows cast by distant quasars that we catch glimpses of WIM faint fingerprints. But WIM might not be the only hiding place. Another theory points to cosmic filaments, the colossal highways of dark matter that guide galaxies into clusters. These filaments could be laced with baryons, trapped in vast, diffuse rivers too faint to spot. Imagine trying to find a single lit match in a foggy forest. That's the scale of the challenge astronomers face. Recent simulations suggest these filaments might contain enough gas to fill the gap, but proving it means detecting something barely there, a whisper in a thunderstorm. There's also the unsettling possibility that some baryons are locked in unexpected forms, perhaps as rogue planets drifting in intergalactic space, or even as primordial black holes too small to detect. Some researchers even speculate that a fraction could be tied up in exotic particles we haven't yet discovered, blending the line between ordinary and dark matter. Every hypothesis pushes the boundaries of what we consider normal, forcing us to rethink how matter behaves on the grandest scales. The hunt for these missing baryons isn't just academic. Solving the puzzle could rewrite the cosmic ledger, revealing how galaxies form, how the universe's structure evolved, and even how elements spread through space. New telescopes like the upcoming Athena X-ray Observatory might finally shine a light on these shadowy reservoirs, turning theoretical guesses into hard data. Until then, the missing baryons remain a humbling reminder. Even the stuff we think we understand can slip through our fingers, hiding in plain sight. The Eridanus supervoid might hold the key to the CMB cold spot, but not in the way we first assumed. Picture this void as a titanic bubble of near-nothingness, stretching across 1.8 billion light-years, so vast that light takes billions of years just to cross its emptiness. Normally, such voids would leave only a faint chill in the cosmic microwave background, but the cold spot's temperature drop is far more extreme than the void alone can explain. It's like walking into a walk-in freezer and finding it colder than the vacuum of space itself. Something else must be at work here. One provocative idea is cosmic texture, an exotic defect in space-time left over from the universe's earliest moments. Imagine the young cosmos as molten glass cooling rapidly. As it hardens, tiny cracks might form in its structure. These imperfections, if they exist, could warp the fabric of reality, bending light and subtly draining energy from the CMB in ways that create localized cold spots. The math suggests such textures could mimic the cold spot's profile, but there's a catch. No one's ever detected one directly. They're ghosts in the machinery of the cosmos, theoretical fingerprints of a reality more complex than we ever imagined. Then there's the multiverse angle. If our universe isn't alone, if it's just one bubble in a frothing sea of universes, then perhaps the cold spot is a bruise from a collision with another reality. Think of it like two soap bubbles briefly touching. Where they meet, energy transfers, leaving behind a mark. In this case, the energy drain from such a collision could have cooled the CMB in this precise region. Some simulations even show that universe bubble collisions would create patterns eerily similar to the cold spot's shape and depth, but skeptics aren't convinced. They argue the cold spot could still be a statistical fluke, an improbable but natural fluctuation in the CMB's haze. After all, when you're mapping something as vast as the universe, even the unlikeliest anomalies might pop up purely by chance. The problem: the odds of this particular cold spot appearing randomly are less than 1 in 50,000. That's like flipping a coin and getting heads 50,000 times in a row. Possible, but so unlikely it strains credulity. The debate rages because the stakes couldn't be higher. If the cold spot is proof of cosmic texture or a multiverse collision, it would rewrite our understanding of reality itself. But if it's just a void with hidden properties, it still forces us to admit how little we grasp about the universe's large-scale structure. Either way, this enigmatic patch of cold isn't just a curiosity, it's a cosmic riddle, daring us to question everything we think we know about the nature of existence. What if our universe is just one page in an infinite cosmic library? The multiverse hypothesis suggests exactly that the edge of our observable universe might not be a true boundary at all, but a horizon beyond which entirely separate universes float like bubbles in an unimaginably vast foam. Picture this: each bubble operates under its own unique physics, some with gravity 10 times stronger than ours, others with light that moves at a crawl, and still others where time flows backward. Our universe's laws might feel absolute, but they could be nothing more than a local ordinance in a sprawling cosmic metropolis. The idea of bubble universes springs from theories like eternal inflation, where the fabric of space-time expands at breakneck speeds, spawning new universes in its wake like bubbles forming in a boiling pot. Each bubble nucleates with its own random conditions, creating pocket realities where the fundamental constants, the strength of gravity, the mass of electrons, could be wildly different. Some might collapse instantly, while others thrive for billions of years. Our universe just happens to be one where the numbers lined up right for galaxies, stars, and life. But here's the catch. These other universes aren't just far away, they're entirely disconnected from our space-time, forever beyond our reach. String theory takes this even further, proposing a landscape of possible universes numbering 10 to the 500 power or more. In this view, the multiverse isn't just a scattering of bubbles, but a labyrinth of higher dimensional membranes vibrating in an 11-dimensional bulk. Collisions between these brains could trigger big bangs, meaning our universe might be the aftermath of a cosmic fender bender. Some theories even suggest that the mysterious cold spot in the CMB could be a bruise from such a collision, a scar left by a neighboring universe brushing against ours in the distant past. Yet for all its imaginative power, the multiverse hypothesis has one glaring weakness: no direct evidence. These other universes, by definition, exist outside our causal reach. We can't observe them, measure them, or test their existence in any conventional way. Critics argue this makes the idea unfalsifiable, more philosophy than science. But supporters counter that indirect clues might lurk in anomalies like the CMB's axis of evil or the universe's unexpected flatness, hints that our cosmos was shaped by forces beyond its borders. The multiverse forces us to confront a humbling possibility: that everything we call reality is just a tiny sliver of existence, a single thread in a tapestry too vast to comprehend. Whether it's real or not, the idea alone stretches the imagination, reminding us that the universe's edges might not be edges at all, just the limits of what we're able to see. And beyond that horizon, who knows what else might be waiting? We often picture the Big Bang as a cosmic explosion, a fiery burst flinging matter outward like shrapnel from a bomb. But this mental image is fundamentally wrong. The Big Bang wasn't an eruption in space, it was the explosive birth of space itself, unfolding everywhere at once. Imagine blowing up a balloon covered in dots. As it inflates, every dot moves away from every other dot, not because they're traveling across the rubber, but because the fabric between them stretches. That's closer to what the Big Bang really was: an expansion of spacetime from an unimaginably dense state, carrying galaxies along for the ride. So where's the edge? Here's the twist: there might not be one. If the universe is infinite, it was always infinite, even at the moment of the Big Bang. The difference was how tightly packed everything was. Picture an endless sheet of graphing paper shrinking down so the grid lines become impossibly close together. But no matter how small it gets, the sheet never stops being infinite. That's the paradox. The universe could be boundless without edges, yet still expand. But if the Big Bang happened everywhere simultaneously, does that mean we're at the center? Not at all. In an infinite universe, every point is the center from its own perspective. It's like standing in a forest and seeing trees stretch equally in all directions. No matter where you stand, the view looks the same. This is why the cosmic microwave background appears uniform in every direction. The afterglow of the Big Bang surrounds us because we're inside it, not looking back at some distant origin point. Some theories suggest a finite universe without edges, like the surface of a balloon. If you traveled far enough in one direction, you'd eventually loop back to where you started, not because you hit a wall, but because space curves in on itself. But here's what keeps cosmologists awake at night. We still don't know which model is correct. The universe's geometry appears flat to our measurements, but that could mean it's either infinite or so vast that its curvature is undetectable, like an ant unable to sense the curve of the Earth. The deeper we probe, the stranger it gets. Quantum fluctuations in the early universe might have stretched to cosmic scales during inflation, creating wrinkles in space-time so vast we perceive them as galaxy clusters. And if the multiverse is real, our Big Bang could be just one bubble in a frothing sea of universes, each with its own edge that isn't an edge at all, just a boundary we can't cross. The Big Bang didn't happen at a single point. It happened everywhere, and the edge we think we're chasing might be nothing more than a trick of perspective, a horizon not of the universe but of our own understanding. Time might feel like an unshakable constant, an endless river flowing from past to future, but at the edge of the universe, even this fundamental force could meet its demise. Picture a clock ticking slower and slower until the hands finally freeze, not because they've broken, but because time itself has run out of reasons to move forward. This isn't science fiction. It's one of the grim fates cosmologists call the Big Freeze, a scenario where the universe expands forever, scattering matter so thin that stars can no longer form, black holes evaporate, and the last flickers of heat dissolve into absolute zero. In this frozen twilight, entropy, the universe's relentless slide toward disorder, reaches its peak. Every atom is isolated, every reaction exhausted, and the cosmos becomes a static graveyard where nothing changes because nothing can change. Time, in any meaningful sense, would cease to exist, but entropy isn't the only executioner on the cosmic stage. The Big Rip offers a far more violent finale, where dark energy's grip grows so strong that it doesn't just push galaxies apart, it shreds reality itself. First, galaxy clusters would be torn asunder, then individual galaxies, then stars, planets, and even atoms. In the final microseconds, space-time would fracture into fragments too small to measure, and with no connected fabric left to define, before or after, time would lose all meaning. It's the ultimate cosmic demolition, where the very scaffolding of existence collapses. Yet some theories suggest time's end might not be universal. In a multiverse, pockets of reality could experience time differently, some freezing, others ripping apart, while a lucky few might cycle into new beginnings. Quantum fluctuations near the edge of a dying universe could even spawn new Big Bangs, birthing fresh timelines like buds on a cosmic branch. The catch. For us, trapped in our own bubble of causality, the boundary between time and no time would be a one-way door. Once crossed, there's no turning back, no observer, no memory, no physics left to mark its passing. The chilling truth is that time might not be a feature of the universe, but a side effect of its activity. Like the sound of a running engine that goes silent when the fuel runs out, time could simply be the universe's way of tracking change, and when change is no longer possible, time might vanish without a trace. Whether through freezing, ripping, or some unknown metamorphosis, the edge of reality could be the one place where even the most fundamental forces finally, quietly, give up. The Fermi paradox has haunted astronomers for decades. If the universe is teeming with potential life, why haven't we heard so much as a whisper? One chilling answer might lie at the edge of the cosmos itself. Imagine a civilization so advanced that it's no longer bound by the limits of their home star system. Over billions of years, as their local resources dwindle, wouldn't the logical next step be to migrate toward the universe's expanding frontier, where untapped energy and raw materials flow like cosmic rivers? The universe's accelerating expansion creates a paradox of its own. While galaxies at the edge are being pulled away faster than light can bridge the gap, the space between them is also stretching, opening vast new regions for colonization. Advanced civilizations might see these horizons not as barriers, but as opportunities, building megastructures near the cosmic cliffs where matter is freshly distributed, or tapping into the energy of inflationary space itself. If life tends to follow the path of least resistance, then the real action might not be in the crowded galactic cores, but out there where the universe is still writing its own rules. This could explain the eerie silence. Civilizations capable of harnessing the energy of stars or black holes wouldn't just linger in their cradle, they'd expand outward like explorers chasing the horizon. By the time a species like ours develops the technology to listen for signals, the most advanced societies might already be gone, having leapfrogged toward the universe's ever-receding edge. Their transmissions, if they even bother with such primitive communication, could be racing toward regions of space we'll never see, lost in the widening gulf between expanding cosmic shores. There's another, darker possibility. The edge of the universe isn't just a land of opportunity, it's also a survival imperative. As dark energy accelerates the cosmos's expansion, clusters of galaxies will eventually be torn apart, leaving island universes isolated in an endless void. Any civilization aware of this fate would have an existential incentive to stay ahead of the curve, constantly migrating toward regions where gravity still holds sway. The silence we perceive might not be indifference, it could be a cosmic diaspora, a silent exodus toward the only places where long-term survival is still possible. But this raises an even more unsettling thought. If the universe's expansion is inevitable, then all civilizations, no matter how advanced, are ultimately racing against the same entropic clock. The edge isn't a fixed destination, it's a moving target, slipping further away with every passing moment. Perhaps the Great Filter isn't some catastrophic event in our past, but a slow, inescapable reality that the universe itself is designed to isolate and extinguish intelligent life, scattering it across an ever-expanding desolation until the last embers of thought flicker out in the endless dark. Or maybe we're just early. The universe is still young by cosmic standards, and the civilizations destined to dominate the far future might not have even arisen yet. While we strain to hear whispers in the void, the real conversation could be waiting for a time when the cosmos is richer, colder, and far stranger than anything we can imagine. Either way, the edge of the universe isn't just a boundary, it's a mirror, reflecting back our deepest fears about what it means to be alone in an infinite expanse. The shape of the universe isn't just a cosmic curiosity, it's the ultimate roadmap, telling us whether space stretches on forever, loops back on itself, or bends in ways that defy our three-dimensional intuition. Imagine holding a sheet of paper perfectly flat in your hands. No matter how far you travel across its surface, you'll never loop back to where you started. That's a flat universe. Now crumple that paper into a ball. Walk far enough in one direction, and you'd eventually return to your starting point, a closed, spherical cosmos. But there's a third option, a saddle-shaped universe, twisting outward in opposite directions like a giant Pringle chip, where parallel lines diverge and the angles of triangles add up to less than 180 degrees. This isn't just geometry, it's the key to understanding whether the universe has an edge. If space is flat or saddle-shaped, it could stretch infinitely, meaning there's no boundary, no outside. But if it's spherical, the cosmos might be finite, like the surface of Earth, no edges, just an endless loop. The wild part, we've measured the universe's curvature with astonishing precision, studying the cosmic microwave background for subtle warps in spacetime. So far, the data suggests it's flat to within a razor-thin margin of error. But flat doesn't necessarily mean infinite, just that any curvature is too slight for us to detect, like an ant failing to notice the Earth's curve beneath its feet. A spherical universe would have mind-bending implications. Travel far enough in one direction, and you'd circumnavigate the cosmos like Magellan sailing around the globe, except you'd end up where you began without ever hitting a wall. Meanwhile, a saddle-shaped universe would be a hall of mirrors on a cosmic scale, where light bends unpredictably and distant galaxies appear warped like reflections in a funhouse. But the shape isn't just about edges, it's about fate. A closed universe would eventually collapse in a big crunch, gravity pulling everything back into a singularity. A flat or open universe, though, could expand forever, succumbing to dark energy's relentless push. The universe's geometry is its destiny, written in the fabric of spacetime itself. And here's the twist: even if the cosmos is flat today, that might not always be true. Some theories suggest dark energy's influence could warp space over trillions of years, subtly bending the universe into a new shape we can't yet predict. So when we talk about the edge of the universe, we're really asking whether edges exist at all. The answer might be stranger than we think, not a wall or a void, but a cosmic Möbius strip turning back on itself in ways that make edge meaningless. The universe's shape isn't just a trivia question, it's the ultimate riddle hiding in plain sight. What if the entire observable universe, every galaxy, every star, everything we've ever detected, is just a tiny bubble of emptiness floating in a far vaster cosmic ocean? That's the spine-tingling premise of the phantom void hypothesis, a radical idea suggesting we might be living in a local underdensity so enormous it distorts our entire perception of reality. Picture a lone soap bubble adrift in a stormy sea, its thin walls shielding a pocket of calm while chaos rages outside. Now scale that up to cosmic proportions. Our universe, with all its billions of galaxies, might be that bubble, a relatively sparse region in a multiverse where most of space is far denser and more chaotic. This isn't just wild speculation. If true, it could solve two of cosmology's biggest mysteries in one stroke. First, dark energy. The force accelerating the universe's expansion might not be a mysterious property of space itself, but an illusion caused by our bubble's low gravity. In a denser outer multiverse, gravity's pull would be stronger, making galaxies clump together faster. From our sparse vantage point, it would look like something is pushing the universe apart, when in reality, we're just seeing the contrast between our void and the crowded outside. It's like standing on a near-empty train car while the rest of the train is packed. If you didn't know about the crowded cars ahead, you'd assume some invisible force was making your car stretch. Then there's the Hubble tension, the headache-inducing mismatch between how fast we measure the universe expanding nearby versus estimates from the early cosmos. If we're in a void, gravity outside our bubble would tug matter inward, slowing the expansion rate in the larger multiverse. But inside our low-density pocket, there's less gravity holding things back, so galaxies here would appear to flee faster than they should. The discrepancy isn't a flaw in our measurements, it's a cosmic optical illusion, a trick of perspective on the grandest scale imaginable. But how could a void this vast exist without us noticing? The answer lies in the cosmic microwave background. Tiny temperature variations in this ancient light might hold hints of a density gradient, a subtle but telltale sign that one direction of space is slightly emptier than the others. Some researchers claim they've already spotted this in the data, a peculiar dipole asymmetry that could be the shadow of our bubble's edge. Others argue it's just statistical noise, the universe messing with us as usual. The implications are staggering. If the phantom void hypothesis is right, then dark energy might not exist at all, or at least not in the way we think. The accelerating expansion could be a mirage, a side effect of our peculiar cosmic address. And the multiverse wouldn't just be a collection of alternate realities, but a fractal foam of voids and clusters, each with its own physics and fate. We might not be special, but we are isolated, floating in a quiet backwater while the true cosmic drama unfolds beyond our horizon. Of course, not everyone buys it. Critics point out that a void large enough to explain these effects would violate the cosmological principle, the idea that the universe should look roughly the same everywhere. Then again, maybe that's the point. The phantom void hypothesis isn't just a solution to a few puzzles, it's a challenge to our deepest assumptions. If even the laws of physics can change depending on where you stand in the multiverse, then the universe might be far stranger and far more flexible than we ever dreamed. Black holes aren't just cosmic vacuum cleaners, they might be the birthplaces of entire universes. Imagine falling past the event horizon of a supermassive black hole beyond the point of no return. According to the black hole universe theory, you wouldn't be crushed into oblivion. Instead, you'd find yourself in a sprawling new cosmos with its own stars, galaxies, and perhaps even black holes birthing universes of their own. This isn't science fiction, it's a radical twist on physics that suggests our entire universe could exist inside a black hole belonging to a parent universe. The idea emerges from a strange property of black holes, their singularities. At the core of every black hole lies a point where gravity becomes infinite and space-time curves endlessly. But what if that singularity isn't an end but a bridge? Some theories propose that the extreme conditions inside a collapsing black hole could trigger a rebound effect, like a cosmic bounce, creating an entirely new space-time continuum. Picture a Russian nesting doll where each layer hides another universe inside, all the way down. This ties into conformal cyclic cosmology, a mind-bending model proposed by physicist Roger Penrose. He suggests that universes don't just end, they reset. As one universe expands toward heat death, its particles lose energy and become indistinguishable from the low-energy particles of a newborn cosmos. The end of one universe could be the Big Bang of another, linked through black holes like cosmic conveyor belts. Imagine a phoenix made of space-time, endlessly dying and being reborn from its own ashes. Then there's the holographic principle, which throws another curveball. It suggests that all the information in our three-dimensional universe might be encoded on a two-dimensional surface, like a cosmic DVD where the film we experience is just a projection. If true, the event horizon of a black hole could act as that surface, storing the data of everything that falls inside. In other words, our universe might not just be inside a black hole, it could be a hologram painted on its edge. Critics argue there's no way to test these ideas, since anything crossing a black hole's event horizon is lost to us forever. But supporters point to faint echoes in the cosmic microwave background, circular patterns Penrose calls Hawking points, which he claims are scars from previous universes. Whether these are real or just cosmic static is hotly debated. What's undeniable is the theory's poetic symmetry. Black holes, the darkest objects in existence, might also be the brightest nurseries of creation. If the black hole universe theory is correct, it means every black hole in our cosmos could contain an entire universe, each with its own laws and constants. Some might be stillborn, collapsing instantly, while others thrive for billions of years. And if those universes contain black holes of their own, the cycle could repeat infinitely, a fractal of realities within realities. It's a humbling thought that we might not be at the top of the cosmic food chain, but just one layer in an endless descent into the unknown. This idea forces us to rethink the very nature of existence. If universes can be born inside black holes, then our search for the edge of the cosmos might be fundamentally misguided. There might not be an edge at all, just an infinite regression of worlds within worlds, each hidden behind an event horizon we can never cross. The ultimate boundary of reality could be something far stranger, not a wall, not a void, but a doorway, one that leads not outward but inward forever. The boundary of our universe might not be the beginning of everything, it could be the echo of something far older. What if the Big Bang wasn't the absolute start, but just the latest chapter in an endless cycle of cosmic rebirth? This is the heart of Roger Penrose's conformal cyclic cosmology, a theory so audacious it suggests our universe's edge might bear scars from past realities. Imagine a cosmic palimpsest where the faint imprints of long-dead universes are etched into the fabric of space-time itself, waiting to be decoded. Penrose's idea hinges on a peculiar symmetry. As the universe expands toward heat death, a state where all matter decays into radiation and distances grow incomprehensibly vast, the immense scale actually starts to resemble the unimaginably tiny conditions of the Big Bang. It's like zooming in on a snowflake until its intricate branches blur into a single point, then zooming out to find they've reformed into a new, identical flake. At these extremes, the distinction between end and beginning melts away, allowing one eon's demise to seed the next's birth. The evidence, strange circular patterns in the cosmic microwave background that Penrose calls Hawking points, ghostly signatures of supermassive black holes from a prior universe, their final explosions imprinted like fingerprints on our sky. But there's another vision of cosmic origins, Stephen Hawking's no-boundary proposal. Picture the universe not as an exploding firework, but as a smooth, self-contained surface with no sharp edges, like the rounded bottom of a wine glass. In this model, time and space curve back on themselves at the Big Bang, meaning there's no before, because there's no boundary to cross. It's a universe that creates itself from pure geometry, where asking what existed prior is like asking what's north of the North Pole. The edge isn't a wall, it's a fold, a seamless transition from nothingness into everything. What both theories share is a radical rethinking of boundaries. Whether through endless cycles or self-contained loops, they suggest the universe's edge isn't a limit but a gateway, a place where the line between destruction and creation blurs. Recent observations of anomalous heat spots in the CMB lend tentative support to Penrose's claims, while quantum gravity models inch closer to Hawking's mathematical elegance. Yet the debate is far from settled. Critics argue these ideas stretch known physics to its breaking point, trading testable predictions for poetic grandeur. But consider this: if our universe truly carries remnants of its ancestors, then the answers to cosmology's deepest questions might not lie ahead, but behind, written in the fading glow of cosmic dawns we can barely comprehend. The edge of reality might not be a barrier at all, but a mirror reflecting infinite iterations of existence, each one rewriting the rules of what's possible. While the cosmic microwave background gets all the attention, there's another, far more elusive fossil from the dawn of time, a sea of nearly massless particles called neutrinos, streaming through the universe like silent whispers from the edge of reality. These cosmic ghosts were born just 1 second after the Big Bang, making them the oldest known messengers from the universe's infancy. Unlike the CMB's afterglow, which took 380,000 years to emerge, the neutrino background carries secrets from a time when the cosmos was still a seething, opaque plasma, hotter than the core of a star. Detecting these relic neutrinos is like trying to catch smoke with your bare hands. These particles barely interact with matter. Trillions pass through your body every second without a single collision. They're so insubstantial that even a block of lead light-years thick wouldn't stop most of them, and yet their very elusiveness makes them priceless. Neutrinos from the early universe have been traveling virtually undisturbed for 13.8 billion years, meaning they hold a pristine record of conditions mere moments after creation. If we could read them, they'd reveal how the infant cosmos behaved when it was smaller than a grapefruit, long before atoms or light could exist freely. The challenge: these primordial neutrinos have been stretched to near undetectable energies by the universe's expansion. Today, they drift through space with barely a whisper of warmth, just a fraction of a degree above absolute zero. Spotting them would require detectors the size of planets, chilled to temperatures colder than deep space. Some scientists propose hunting for their faint imprints in the cosmic microwave background, where their presence might subtly warp the polarization of ancient light. Others dream of capturing their rare interactions in vats of ultra-pure liquid argon buried miles underground. But why go through all this trouble? Because neutrinos could be the key to unlocking the universe's first second, a time when gravity, matter, and energy danced in ways we can only simulate. They might carry clues about why matter triumphed over antimatter, or whether undiscovered particles once roamed the early cosmos. And if we ever detect them, it would be like finding a letter sealed at the dawn of time, addressed directly to us. Until then, the neutrino background remains the universe's oldest secret, a shadowy archive drifting just beyond our grasp, waiting for the day we finally learn how to listen. At the absolute limits of the cosmos, where distances stretch beyond comprehension and gravity warps space-time into knots, the universe might not be smooth at all. Instead, it could be seething with a chaotic froth known as quantum foam, a turbulent ocean of microscopic spacetime bubbles constantly forming and vanishing in the blink of an eye. Imagine zooming in on the fabric of reality until it dissolves into a frenzy of tiny, flickering distortions. At this scale, spacetime isn't the serene continuum we perceive, it's a boiling storm where nothing is fixed, and even the concepts of here and now lose all meaning. This turbulence isn't random, it's governed by the Planck length, an almost unimaginably tiny distance where the rules of quantum mechanics and general relativity collide. At scales this small, spacetime itself becomes grainy, like the static on an old television screen. Particles and energy pop in and out of existence, borrowing from the vacuum of space before vanishing again. Under these conditions, wormholes, hypothetical tunnels through space-time, might flicker into being for mere fractions of a second, offering fleeting shortcuts across the universe before collapsing under their own instability. It's as if the cosmos is constantly stitching and unstitching its own fabric, weaving threads of possibility too brief for us to grasp. Some theories suggest these quantum foam fluctuations could explain the universe's most baffling phenomena. Dark energy, for instance, might not be a mysterious force at all, just the cumulative effect of countless microscopic spacetime bubbles pushing the cosmos apart from within. Even black holes, those cosmic vacuum cleaners, could have event horizons fizzing with quantum foam, their singularities obscured by a froth of microscopic wormholes and virtual particles. The foam could act as a cosmic buffer, preventing the infinite densities predicted by classical physics and replacing them with something far stranger, a fractal dance of creation and annihilation. But here's the catch: we can't observe quantum foam directly. The Planck length is 1 billion times smaller than a proton, far beyond the resolution of any microscope or particle collider. Instead, scientists look for indirect clues, subtle anomalies in gamma-ray bursts or distortions in the light from distant quasars that might hint at spacetime's grainy nature. Some experiments even aim to detect minute changes in the speed of light caused by quantum foam's fluctuations, like ripples distorting a perfect wave. If quantum foam is real, it forces us to rethink the very nature of reality. The smooth, predictable spacetime we take for granted could be an illusion, a large-scale approximation that hides the universe's frantic, chaotic heart. At the edge of the observable cosmos, where distances stretch toward infinity, spacetime might not just bend, it could shatter into a wilderness of possibility, where the familiar laws of physics dissolve into pure potential. Quantum foam doesn't just mark the boundary of our understanding, it could be the foundation of existence itself, whispering that the universe is far wilder than we ever dreamed. What if everything we see, every galaxy, every star, even our own thoughts, is nothing more than a projection, a cosmic illusion painted on the boundary of reality itself? This is the startling promise of the holographic principle, the idea that our three-dimensional universe might actually be encoded on a two-dimensional surface at its edge, like a movie projected from the walls of a theater. Imagine taking all the information that makes up your body, your memories, even the atoms in the air you breathe, and compressing it into a flat, shimmering mural on the fabric of spacetime. According to this theory, the universe isn't just in space, it is space, an elaborate hologram where depth and dimension are tricks of perspective. The math behind this mind-bending concept comes from an unlikely pairing: black holes and quantum theory. In the 1990s, physicist Leonard Susskind realized that the information swallowed by a black hole couldn't truly vanish. It had to be preserved somehow, in line with quantum mechanics' strict no-deletion policy. But where? The answer emerged when researchers noted that the information content of a black hole's interior scales not with its volume, but with the area of its event horizon. In other words, everything inside could be perfectly described by data imprinted on the surface, like a cosmic barcode. This led to a radical leap. If black holes work this way, maybe the entire universe does too. The most concrete version of this idea comes from the AD-S/CFT correspondence, a mathematical bridge between two seemingly unrelated theories. On one side, there's anti-de Sitter space, a hypothetical universe with negative curvature, where gravity behaves in strange, geometric ways. On the other, conformal field theory, a framework for describing particles and forces without gravity at all. The correspondence suggests these are two sides of the same coin. A high-dimensional gravitational universe like ours could be equivalent to a lower-dimensional quantum theory operating on its boundary. Picture a soap bubble. The swirling colors and reflections on its surface might seem like mere decoration, but in reality, they encode the precise shape and motion of the entire bubble. Similarly, our 3D cosmos could be a shadow of a 2D reality playing out at the edge of existence. If this sounds like science fiction, consider the implications. First, it would mean that space itself is emergent, not fundamental, but something that arises from deeper, more primal interactions, much like temperature emerges from the motion of atoms. Second, it challenges our intuitive sense of location. The laptop in front of you, the trees outside your window, they might not truly be where you perceive them. Instead, their essence could be flickering patterns on a distant horizon, translated into the illusion of depth by the laws of physics. Yet the holographic principle isn't just philosophical musing. It's a practical tool, helping physicists tackle problems in quantum gravity and black hole thermodynamics that were once thought unsolvable. By translating messy 3D gravitational puzzles into cleaner 2D quantum ones, researchers have gained startling insights, like how information might escape a dying black hole via quantum hair etched onto its surface. Some even speculate that dark energy, the force accelerating cosmic expansion, could be a side effect of the universe's holographic nature, its boundary subtly tugging at the fabric of spacetime from afar. Of course, skeptics remain. The AD/S/CFT correspondence works beautifully in mathematical toy universes, but our cosmos doesn't have the convenient negative curvature of anti-de Sitter space. Proving the principle in the real world would require detecting telltale signatures in the cosmic microwave background or quantum foam, hints that spacetime itself has a pixelated structure at the tiniest scales. So far, no such evidence has emerged, but the search continues. Whether or not the holographic principle holds, it forces us to confront a humbling possibility. That reality might be far stranger and far more interconnected than our senses suggest. The edge of the universe, if this theory is correct, isn't just a boundary, it's the canvas on which all of existence is painted, a mirror reflecting not just what we are, but how we're made. And if that's true, then every star, every atom, every fleeting thought might be nothing more, and nothing less than a ripple on the surface of the infinite. Somewhere beyond the farthest galaxies we can see, something impossible is happening. Entire clusters of galaxies are streaming in the same direction at unimaginable speeds, as if pulled by an invisible force outside our universe. This is dark flow, one of cosmology's most unsettling discoveries. Picture throwing confetti into the air, only to watch every piece drift toward the same hidden magnet, defying gravity's pull. That's the scale of what we're dealing with, thousands of galaxies caught in a cosmic current we can't explain. The mystery began when researchers studied the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature shifts in this ancient light revealed something bizarre. Galaxy clusters weren't just moving randomly, they showed a coordinated drift toward a single patch of sky near the constellations Centaurus and Vela. At first, scientists assumed it was a measurement error, but the data held up, revealing velocities of nearly 2 million miles per hour, far too fast to be caused by known gravitational forces within our observable universe. This raises two spine-tingling possibilities. First, dark flow might be evidence of massive structures beyond our cosmic horizon, superclusters so enormous their gravity reaches across the void, tugging at everything in their path. Imagine standing on a beach, feeling the oceans pull long before you see the waves. These unseen giants could be the cosmic equivalent lurking just out of sight. The catch, according to standard cosmology, the universe's expansion should make such large-scale structures impossible beyond the observable bubble. Their existence would shatter our understanding of how matter clumps together after the Big Bang. Then there's the radical alternative. Dark flow could be proof of other universes. In multiverse theories, our cosmos might be one bubble in an endless foam of realities, each with its own physical laws. If a neighboring universe brushed against ours in the distant past, its gravity might still be drawing matter toward the collision point, like a fingerprint pressed into spacetime. Some models even suggest these parallel universes could have higher dimensions, allowing their gravity to leak into our reality in ways we can't directly detect. Critics argue the dark flow signal might just be noise, an artifact of incomplete data or systematic errors in how we measure galaxy motions. But follow-up studies, including observations by the Planck satellite, only deepen the puzzle. The flow extends farther than expected, spanning billions of light years, with no clear source within our observable realm. If it's not a fluke, then something fundamental is missing from our cosmic equations. Perhaps the most unsettling implication is what dark flow says about the universe's symmetry. The cosmological principle, the bedrock assumption that the cosmos looks roughly the same everywhere, starts to crumble if entire swaths of space are marching in lockstep toward an unseen attractor. It's as if we've spent centuries studying a vast, still ocean, only to suddenly notice the water is all flowing downhill toward a drain we can't see. Whether dark flow is a phantom signal or a glimpse of something transcendent, it forces us to confront the limits of our knowledge. The universe might not just be stranger than we imagine, it could be stranger than we can imagine, with currents flowing to shores beyond the edge of existence itself. And if we ever trace this cosmic river to its source, we might find not just answers, but questions that redefine reality as we know it. What if the universe isn't just a vast, endless expanse, but a shape so strange it turns the very idea of an edge into an illusion? Picture this: you're an ant crawling on the surface of a donut. No matter how far you walk, you never hit a wall, just an endless loop where forward eventually brings you back to where you started. Now imagine that donut isn't a tiny snack, but the entire cosmos curled into a shape mathematicians call a torus. This isn't just a whimsical thought experiment, it's a real possibility in cosmology, where the universe's topology, its hidden geometry, could be anything but simple. The clues lie in the cosmic microwave background, that ancient light from the dawn of time. If the universe were a torus, light traveling in one direction would eventually loop around and return from the opposite side, creating faint, repeating patterns in the CMB like echoes in a cosmic hall of mirrors. Astronomers have scoured the data for these ghostly duplicates, matching circles of temperature fluctuations that would betray the universe's true shape. So far, none have been found, but that doesn't rule out more exotic topologies. The cosmos could be twisted like a Möbius strip, where a full loop flips left and right, or even a hyperbolic kaleidoscope, where parallel lines spiral apart in ways that defy Euclidean logic. Then there's the three torus, a mind-bending structure where space folds back on itself in all three dimensions. In such a universe, if you peer deep enough through a telescope, you might see multiple copies of the same galaxy, each one a ghostly repetition from light that circumnavigated the cosmos. It's like standing between two mirrors, watching your reflection repeat into infinity, except here the reflections are real and the mirrors are the fabric of space-time. The eerie part: if this topology is real, the universe could be finite yet unbounded, meaning you'd never find an edge no matter how far you traveled. But why does topology matter? Because it reshapes our understanding of boundaries. In a toroidal universe, the edge isn't a place, it's a perspective. What looks like a distant horizon might just be the same patch of space, viewed from another angle after light's epic journey around the cosmic loop. Even the Big Bang's location would be up for debate. If space curls back on itself, the explosion happened everywhere, not at a single point. The donut universe doesn't just challenge our sense of scale, it forces us to rethink the nature of beginnings and endings altogether. Of course, not all topologies are so tidy. Some theories propose a chaotic, multiply-connected cosmos, riddled with wormhole-like shortcuts and topological defects, kinks in space-time left over from the universe's violent birth. In such a reality, the edge might not be a smooth curve but a fractal labyrinth, where every turn reveals new layers of complexity. others speculate that quantum fluctuations could make spacetime foam like on the tiniest scales, a seething turbulence where geometry itself is uncertain. The wildest implication, if the universe's topology isn't what we assume, our entire cosmic map could be wrong. Distant galaxies might be closer than they appear, or far more distant depending on how spacetime folds. Dark energy's effects could be warped by unseen curvature, and even the universe's apparent flatness might be a local quirk, like mistaking a mountain valley for the whole Earth. The topology isn't just a curiosity, it's the hidden code shaping everything we observe. So while we hunt for clues in the CMB's subtle patterns, one thing is clear: the universe's shape is more than a geometry puzzle. It's a key to unlocking whether edges exist at all, or if they're just illusions in a cosmos far stranger and far more cleverly connected than we ever dreamed. Black holes aren't just cosmic vacuum cleaners, they're also the ultimate shredders of information, swallowing stars, planets, and even light, seemingly erasing them from existence forever. But here's the paradox: quantum mechanics insists that information can never truly be destroyed. So where does it all go? This puzzle isn't just confined to black holes. It might hold the key to understanding the very edge of our universe. Imagine the universe as a cosmic hard drive, encoding every event, every particle collision, every thought that's ever occurred. At a black hole's event horizon, this information appears to vanish, compressed into a singularity where spacetime breaks down completely. Yet quantum mechanics insists it must still exist somewhere, even if scrambled beyond recognition. Now scale that up to the universe itself. If the cosmos has an edge, or even an effective boundary like the cosmic horizon beyond which light can never reach us, what happens to the information of everything that crosses it? Does it pile up like data on a celestial hard drive, or does it dissolve into nothingness, rewriting the rules of physics in the process? This is where things get truly mind-bending. Some theories suggest the universe's edge could behave like a black hole's event horizon, a point of no return where information is preserved in some form, even if we can't access it. The holographic principle, for instance, proposes that all the information within our three-dimensional reality might be encoded on a two-dimensional surface at the universe's boundary, like a cosmic DVD where the movie of existence is stored on its outer shell. If true, then nothing is ever truly lost. It's just translated into a form we can't yet decipher. But there's a darker possibility. If dark energy's acceleration continues unchecked, distant galaxies will eventually cross our cosmic horizon, their light stretched so far that it becomes undetectable. In this scenario, the universe isn't just expanding, it's actively erasing information from our view, like pages torn from a book and set aflame. Unlike a black hole, where information might be preserved behind the event horizon, this cosmic deletion could be permanent, with no higher dimensional surface to save it. The universe's edge wouldn't be a storage device, it would be a shredder, grinding the past into unrecoverable noise. Yet there's a twist that keeps physicists up at night. Quantum gravity models hint that spacetime might be fundamentally pixelated, built from tiny, indivisible units that prevent true information loss. In this view, even at the universe's edge, data isn't destroyed, it's recycled, repurposed into the fabric of new spacetime. Picture an endless cosmic loom, weaving the threads of expired realities into the tapestry of the future. If correct, this would mean the universe's boundary isn't a wall, but a transformer, converting the past into raw material for whatever comes next. The stakes couldn't be higher. If information can vanish at cosmic scales, it would upend not just quantum theory, but our understanding of causality itself. Events near the edge might leave no trace, rendering them as unverifiable as dreams. Conversely, if information is preserved, the universe might contain hidden archives of everything that's ever happened, a library of reality waiting to be decoded. The paradox forces us to confront a haunting question. Is the universe's edge the ultimate vault or the ultimate void? And if we ever find the answer, it might not just change physics, it could redefine what it means to exist at all. At the very edge of reality, where the universe thins into nothingness and the laws of physics fray, there's a thought experiment so unsettling it shakes our understanding of existence itself. Picture a single, disembodied brain complete with memories, thoughts, even the illusion of a body floating in the void, conjured into being by nothing more than a random quantum fluctuation. This is the Boltzmann brain paradox, a cosmic riddle that forces us to question whether we're the products of orderly evolution or just fleeting accidents in an endless sea of chaos. The paradox comes from thermodynamics, specifically the idea that given enough time, even the most improbable events will eventually happen. In an infinite or near-infinite universe, particles bouncing around at random could spontaneously arrange themselves into a conscious mind, complete with false memories of a past that never existed. Statistically, these phantom brains should outnumber real, biologically evolved minds by an unimaginable margin. So if the universe truly has no edge, if it stretches forever into space and time, why aren't we all Boltzmann brains momentarily convinced of our own reality before dissolving back into the void? This isn't just philosophical musing. The paradox cuts to the heart of cosmology's biggest questions. If the universe at its edges is cold, empty, and eternal, then randomness becomes the dominant force. Given infinite time, even the vacuum of space could, on rare occasions, mimic the complexity of a living brain through sheer chance. Some interpretations of quantum mechanics even suggest these fluctuations might be constantly happening, popping in and out of existence like soap bubbles in a cosmic bath. The eerie implication: the further we look toward the universe's boundaries, the more likely it becomes that we're not the observers but the observed, brief flickers of awareness in a dark, indifferent expanse. But there's a flaw in this nightmare scenario. If Boltzmann brains were common, they'd vastly outnumber real observers like us. So statistically, you should be one of those disembodied illusions, not a living being reading this on a device. The fact that we exist in a seemingly stable, ordered universe suggests something's preventing these random fluctuations from dominating reality. Maybe the universe isn't infinite after all, cutting off the time needed for such freak events. Or perhaps the vacuum of space isn't as unstable as we think, suppressing Boltzmann brains before they can form. The most haunting resolution comes from the multiverse. If our cosmos is just one bubble in an infinite foam of universes, each with different physical laws, then Boltzmann brains might indeed outnumber us, just not here. We find ourselves in a universe where conditions make life sustainable precisely because conscious observers can't emerge in the others. It's a cosmic version of survival bias. We don't see the failed realities where only phantom minds exist because those minds have no stable world to observe. The Boltzmann brain paradox doesn't just challenge our place in the cosmos, it redefines the nature of reality itself. Are we the inevitable products of a finely tuned universe, or just statistical outliers in a void that's constantly dreaming up and discarding consciousness? As we peer toward the universe's edge, we're not just searching for distant galaxies or dark energy. We're staring into a mirror, forced to wonder whether the face looking back is flesh and blood or a trick of the light, destined to fade the moment the universe blinks. What if the edge of the universe isn't a physical boundary at all, but a glitch in the code of a simulated reality? The simulation hypothesis, the idea that our universe might be an artificial construct running on some unfathomable computer, offers a radical explanation for why we can't peer beyond the cosmic horizon. Think of it like a video game. When you approach the edge of a virtual world, the terrain either stops abruptly or repeats endlessly, not because there's nothing beyond, but because the programmers didn't bother rendering what lies outside the player's view. Could our observable universe's 46 billion light-year limit be the same kind of computational shortcut, a cosmic render distance set by whatever or whoever built this simulation? The parallels are unnerving. In virtual environments, rendering distant objects in full detail wastes processing power, so developers use tricks like fog, low-resolution textures, or pop-in effects to hide the illusion. Similarly, the universe's expansion ensures we'll never reach galaxies beyond our horizon, their light stretched into oblivion before it can reach us. It's almost too convenient, as if some system constraint prevents us from accessing regions that haven't been fully computed. Even quantum mechanics' fuzzy nature fits the analogy. At tiny scales, particles behave like partially loaded assets, existing in probabilistic states until observed, as if the simulation only renders definite properties when absolutely necessary. But if we're in a simulation, the edge might not just be a technical limitation. It could be a deliberate design choice. A programmer crafting a universe might wall off certain areas to preserve mystery, conserve resources, or even hide the underlying machinery. Imagine an ant in a terrarium, unaware the glass walls aren't the edge of reality, just the limits of its enclosure. For all we know, our cosmic horizon serves the same purpose. Not a true boundary, but a quarantine keeping us from seeing the strings behind the show. Critics argue that simulating an entire universe down to every atom and quantum fluctuation would require unfathomable energy. Yet proponents counter that even our primitive simulations like video games or climate models use compression and approximations to mimic complexity efficiently. A superintelligent civilization might employ similar tricks, running our reality at a level of detail just fine enough to fool its inhabitants. The universe's apparent smoothness could be a carefully curated illusion, with low-priority regions, like the empty voids between galaxies rendered in lower fidelity to save resources. Then there's the question of intent. If we're in a simulation, the edge might not be an accident but a clue. Some theorists suggest advanced civilizations would embed Easter eggs in their creations, subtle hints meant to provoke curiosity about the true nature of reality. Anomalies like the CMB's axis of evil, the universe's improbable fine-tuning for life, or even dark flow's unexplained pull could be breadcrumbs left by the architects nudging us toward the truth. After all, what's the point of building a universe if no one inside ever questions its walls? The simulation hypothesis forces us to confront a dizzying possibility, that the edge we're chasing isn't a place but a permission setting. The cosmos might not have physical limits, just rules about how much we're allowed to see. And if that's true, then every mystery we've encountered, dark energies push, the missing baryons, even the arrow of time, could be artifacts of the code, glitches in a system far grander than we'll ever comprehend. The real question isn't what lies beyond the horizon, but who, or what decided to draw it there in the first place. The universe isn't just scattered with galaxies, it's woven into an intricate tapestry of light and shadow, a network of threads so vast they make entire superclusters look like tiny knots in a cosmic quilt. These are the filaments of the cosmic web, the largest structures in existence, stretching hundreds of millions of light years across the void like bridges between worlds. But here's what keeps astronomers awake at night. At the very edges of the observable universe, these filaments don't just fade, they dissolve, unraveling into darkness as if snipped by some unseen hand. What happens to them out there, and could these vanishing threads be tethered to something beyond our horizon? Picture the cosmic web as a labyrinth of highways, with galaxies huddled like cities at the intersections. These filaments are made of dark matter, their gravitational pull funneling gas and stars into glowing tendrils that illuminate the emptiness between. But as we look deeper into space and further back in time, we see something eerie. The filaments grow sparser, their glow dimmer, until they taper off into nothingness. It's not just that they're too faint to see, the structure itself seems to fray, like a rope reaching the end of its length. The unsettling question isn't just why, it's what lies past the fray. One possibility is that we're seeing the limits of star formation itself. At the universe's edge, we're peering into an era before galaxies fully formed, when the cosmic web was still a skeleton waiting for flesh. The gas in these primordial filaments might be too diffuse, too pristine, to ignite the fires of creation. But that doesn't explain why some filaments appear cut off, as if they were part of a larger structure now lost to the expanding void. Could they extend beyond our observable bubble, stitching together universes we'll never see? Then there's the dark matter puzzle. These filaments are thought to trace the distribution of dark matter, the invisible scaffold holding the cosmos together. If the filaments vanish at the edge, does that mean dark matter thins out? Or does it simply become invisible in ways we can't yet detect? Some theorists suggest dark matter might behave differently in these extreme zones, clumping into strange configurations or even transitioning into exotic particles. It's like looking at the roots of a tree and realizing they don't end where the soil turns dark. They transform into something else entirely. The most tantalizing idea is that these fraying filaments aren't endings at all, but bridges. In multiverse theories, our cosmic web might be one thread in a vast, interconnected tapestry, with other universes dangling like dewdrops on a spider's silk. The filaments could be cosmic umbilical cords, feeding matter and energy between realities in ways that defy our physics. It's a poetic thought that the edge of our universe isn't a wall but a seam stitched to something unimaginable. Yet for all the speculation, one fact remains chillingly clear. The cosmic web's fringe is a frontier we may never cross. The universe's expansion is carrying these filaments away faster than light can travel, locking their secrets behind an eternal horizon. Whatever they're connected to, whether more of the same or something beyond our wildest dreams, might forever hover just out of reach, a ghostly reminder that the universe's grand design is far larger and far stranger than we'll ever know. Right now, dark energy is the universe's quiet architect, gently pushing galaxies apart. But what if it's not so gentle? What if, instead of maintaining its steady pressure, it grows stronger over time, unstoppable, ravenous, until it doesn't just expand space but shreds it? This is the nightmare scenario cosmologists call the Big Rip, a fate so violent it makes black holes look tame. Picture dark energy as a runaway train, accelerating not just the universe's expansion but its own strength until gravity, matter, even the fabric of reality itself can't hold on any longer. The timeline of this catastrophe reads like a cosmic horror story. First, galaxy clusters, those immense cities of stars bound together by gravity, would be torn apart. Billions of years from now, as dark energies grip titans, even the Milky Way and Andromeda, destined to collide in a fiery dance, would be wrenched back into the void, their stars scattered like dust in a hurricane. Next, individual galaxies would unravel, their stars flung into the darkness faster than light could bridge the gaps between them. Then, as dark energy's power peaks, planetary systems would disintegrate, Earth ripped from the sun, moons from their planets, until every world floated alone in an infinite, empty night. But the horror doesn't stop there. In the final moments, as dark energy's strength surpasses all other forces, even atoms, the building blocks of everything we know would be torn apart. Protons and electrons, once bound by electromagnetic forces, would be stretched beyond their limits, their bonds snapping like over-tightened strings. Space-time itself would fracture into fragments too small to measure, a froth of quantum chaos where the concepts of here and now lose all meaning. The universe wouldn't just end, it would dissolve, erased in a final, unfathomable instant. Here's the chilling part, this isn't just speculative fiction. The equations allow it. If dark energy is what physicists call phantom energy, a hypothetical form that grows denser as the universe expands, then the Big Rip isn't just possible, it's inevitable. Current observations can't yet confirm whether dark energy is constant or intensifying, but the mere possibility sends ripples through cosmology. Some models suggest this crescendo of destruction could happen in as little as 22 billion years, a blink of an eye on cosmic scales. Yet there's a haunting elegance to the Big Rip. Unlike the slow fade of heat death or the crushing reversal of a big crunch, this scenario is a cosmic crescendo, a final, violent act that leaves no ambiguity. No black holes evaporating over eons, no dim embers of dead stars, just a clean, catastrophic end where the universe's very rules are rewritten in its last seconds. It forces us to confront a profound question. Is dark energy a passive backdrop to the cosmos, or something far more dynamic, more alive in its capacity to reshape reality? For now, the Big Rip remains a hypothesis, a shadow on the edge of our understanding. But its very possibility reminds us that the universe's fate isn't just written in the stars, it's woven into the invisible forces we're only beginning to measure. And if the fabric of space-time can be torn, then every galaxy, every atom, every moment of history is more fragile than we ever dared to imagine. At the farthest reaches of the cosmos, where galaxies flee faster than light can chase them, something profound happens to the very fabric of reality. Cause and effect begin to unravel. Imagine tossing a stone into a pond only to watch the ripples freeze mid-spread, their influence halted by an invisible barrier. That's the eerie paradox of causality's edge, where the universe's expansion outpaces the speed of information itself, leaving events forever disconnected, their relationships severed like threads snipped by cosmic scissors. Einstein's relativity insists that nothing can influence anything else faster than light can travel between them. Yet at the universe's horizon, dark energy stretches space so violently that distant galaxies cross a point of no return. Their light, and thus any signal they might send, can never reach us. This creates islands of causality, regions of space forever cut off from one another, where the concept of before and after loses all shared meaning. It's as if the universe is a vast conversation where half the participants suddenly vanish mid-sentence, their words fading into silence before the rest can hear them. But here's where quantum mechanics crashes the party. At the tiniest scales, particles defy classical causality through entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, even if they're light years apart. This seems to flout relativity's speed limit, creating a paradox. How can the universe enforce causality's rules at cosmic scales while blatantly breaking them in the quantum realm? The clash between these two frameworks escalates at the universe's edge. Quantum fluctuations near the cosmic horizon might spawn pairs of virtual particles, one falling inward while the other escapes, a process that over eons could evaporate black holes via Hawking radiation. But what happens when the horizon isn't a black hole's boundary, but the universe's? Does causality fracture entirely, allowing quantum weirdness to override relativity's orderly chain of cause and effect? Some theories suggest that at these extremes, space-time itself becomes a quantum foam, bubbling with microscopic wormholes that bypass causal connections entirely, like secret tunnels through the fabric of reality. This isn't just academic wrestling, it reshapes how we understand time's arrow. In our local universe, entropy ensures eggs crack but never uncrack, memories form but never unform. But at the edge where causality frays, could entropy's rules twist or even reverse? Could there be zones where effects precede causes, where the future influences the past? The equations hint at possibilities too strange to visualize, like echoes arriving before the shout that created them. Perhaps the most unsettling implication is that causality's edge might not be fixed. As dark energy accelerates the universe's expansion, our cosmic horizon shrinks, steadily chopping away chunks of causality's domain. Billions of years from now, even nearby galaxies will vanish behind this curtain, their histories becoming as inaccessible as dreams. The universe's story isn't just being written, it's being erased in real time, one irreversible slice after another. So where does this leave us, staring into an abyss where physics' two greatest theories, relativity and quantum mechanics, refuse to reconcile, each painting a different portrait of reality's limits? The edge of causality isn't just a boundary of space, it's a frontier of understanding where the universe's rulebook crumbles into ambiguity. And the closer we look, the more we realize the laws we cherish might not be universal truths but local ordinances, holding sway only until the cosmos's tides sweep them away. In the unimaginably distant future, when the last star has flickered out and black holes have evaporated into whispers of radiation, a single photon will begin its journey, the final flicker of light in a universe sliding toward absolute zero. It might emerge from the cooling ember of a long-dead white dwarf, or perhaps it will be the last Hawking particle to escape a vanishing black hole's grip. No matter its origin, this photon will drift through an endless void, its path unbroken by dust or gas, because by then, the cosmos will have stretched into an inconceivable thinness, a graveyard of spacetime too vast for even light to fill. Think of it, a universe so cold, so still, that the very concept of time loses meaning. Galaxies are long gone, their stars reduced to faint echoes in the darkness. The once vibrant cosmic web has frayed into nothingness, leaving only this solitary photon, a traveler with no destination, no eyes to perceive it, no atoms left to scatter its glow. It will never strike a surface, never be absorbed or reflected, because by the time it streaks across the void, there will be nothing left to meet it. And yet, this photon's journey holds a strange, haunting beauty. It carries the last imprint of a universe that once teemed with galaxies and supernova, with planets and oceans and civilizations that reached for the stars. Every other trace of those wonders will have faded into the background murmur of radiation, diluted by the relentless expansion of space. But this photon, this one final spark, will for a fleeting moment hold the weight of existence itself, the last whisper of a cosmos that once knew light. What happens when it reaches the end? If the universe truly meets its fate in heat death, then the photon's voyage never truly ends. Space stretches on, infinite and empty, and the photon's wavelength stretches with it, red shifting into oblivion until it dissolves into the background hum of the universe's dying breath. There's no dramatic finale, no cosmic curtain call, just the slow, silent unraveling of energy into a state of perfect equilibrium, where nothing happens and nothing ever will again. But here's the twist: in a universe without observers, does the photon's journey even happen at all? Physics tells us that reality is shaped by interaction, by measurement. With no one left to witness it, does the last photon's flight blur into the void, a story without an audience, a signal without meaning? It's a paradox that lingers at the edge of thought, a reminder that the universe's legacy isn't just in what it leaves behind, but in the act of being seen, remembered, wondered about. And that might be the most profound lesson of all. Long after the last photon fades, long after the cosmos forgets itself, the mere fact that we're here now asking these questions means the universe for a fleeting moment knew itself. We are its eyes, its voice, its memory. The last photon's journey isn't just an end, it's a mirror reflecting back the extraordinary truth that in a cosmos bound for silence, we were the ones who listened. We've journeyed through 30 of the most baffling mysteries lurking at the edge of the universe, from the Great Attractor's invisible pull to the phantom galaxies vanishing into the void, from the Boltzmann brain paradox to the cosmic web's fraying threads. Each one reveals just how little we truly understand about the cosmos's farthest reaches. These aren't just scientific curiosities, they're cosmic breadcrumbs, leading us toward questions that redefine reality itself. Think about it, we live in a universe where dark energy silently tears space apart, where entire galaxies drift toward something we can't see, and where the laws of physics might unravel at the horizon. The cold spot in the CMB, the missing baryons, the eerie alignment of the axis of evil, none of these fit neatly into our textbooks. They're cracks in the foundation of cosmology, hints that the universe is far stranger, far more mysterious than we ever imagined. And here's the humbling truth: we've barely scratched the surface. Every answer we uncover spawns new questions, each more profound than the last. The edge of the observable universe isn't just a boundary, it's a mirror reflecting back the limits of our knowledge. We're like explorers standing on the shore of an endless ocean, straining to glimpse what lies beyond the horizon, only to realize the waves stretch farther than light itself can travel. Yet this isn't a reason for frustration, it's a call to wonder. The fact that we don't have all the answers isn't a failure, it's the most exciting part of being human. We're the only species we know of that can stare into the abyss and dare to ask, what's out there? Every telescope we build, every equation we solve, brings us one step closer to peering past that cosmic curtain. So stay curious. The next great discovery might be lurking in the next dataset, the next observation, the next bold theory that challenges everything we think we know. The universe's greatest mysteries aren't locked away forever. They're waiting just beyond the edge of our understanding for someone like you to help unravel them. And who knows, the answers might be closer than we think. After all, the cosmos didn't put these puzzles here to taunt us, it left them as invitations. The adventure isn't over, it's only just begun.